Today's topic is Ampere Circuital Law. Just like our Gauss law in electrostatics, Gauss law states that the total net flux passing through a closed Gaussian surface is equal to 1 by epsilon naught times the charge enclosed by that Gaussian surface. So which you can also written as E bar dot ds bar is equal to 1 by epsilon naught times the charge enclosed here. So this can also be written as total integration. You can do it if you want the final value, total flux. Now, so this is a Gauss law in electrostatics. This Gauss law is used to determine the electric field due to symmetrical bodies. Remember students, Gauss law can be applied only for symmetrical bodies. Similarly, the Ampere Circuital Law is also used to determine magnetic field due to bodies having symmetry. Symmetrical bodies. So what is the statement of this Gauss law? Similar to the Ampere Circuit Law, similar to Gauss law, here the line of integral of magnetic field over a closed loop is equal to mu naught times the current enclosed by that closed loop. So line of integration of magnetic field over a closed loop is equal to mu naught times the current enclosed by that closed loop. In Gauss law, the closed surface is named as Gaussian surface. In Ampere Circuital Law, the closed loop is called a closed Amperean loop. Now, here, if you take any closed loop, so this is a current carrying conductor carrying some current I. If I want to find out a magnetic field due to this straight current carrying conductor at a distance r from it, so here if I want to find out a magnetic field, so for this you have to create one closed Amperean loop such that it encloses this current. So this will be a circular closed loop of radius r. So what is the magnetic field at this point? Let us say this is B bar. Actually this is a very small magnetic field, and here this will be B bar, B bar, B bar. Magnitude is B bar at any point. So at all these points magnetic field will be B bar only. That's why I told you the Amperian circuital loop can be applied only for symmetrical bodies. Why? Because for symmetrical bodies magnetic field will be constant at a constant distance, at a given distance. So now if you take this small elemental portion, the line of integration means integrate with respect to the length. So now this you can write integrate B bar with respect to the length. So integrate B bar with respect to the length. So this is the differential element. So this is equal to mu naught times the current enclosed by this loop. In this loop how much current is flowing? I current is flowing. So this is the Ampere Circuital Law. Now instead of one current, this is I1, let us say one more wire is kept here which is carrying current I2. This wire is carrying current I3, but this current carrying current I4 downwards, and this current wire is carrying current I5. So what is the Ampere Circuital Law for this diagram? Here we can write the line of integration of B bar dot dl bar is equal to mu naught times the current enclosed here. Here you can see mu naught times the current enclosed by that closed loop. So here if there is only one conductor, you can use this statement. If there are more number of conductors, mu naught times the algebraic sum of the currents enclosed by that closed loop. So here we can write mu naught into, here if you take this are positive and this will become negative. So you can write I1 plus I2 plus I3 minus I4 minus I5. So we have to take the algebraic sum, that means based on the direction of the current flowing through this one, you consider some currents in the positive direction, the currents which are flowing in the opposite direction should be taken as negative. So this is the algebraic sum. So we can write line of integral of b bar dot dl bar is equal mu naught times the current enclosed here, which is the algebraic sum, or you can write mu naught times of sigma I here. Line integral of b bar dot dl, this can also be written as mu naught into h bar, this is a magnetizing field, dot dl bar is equal to mu naught times of I. You can cancel this mu naught and mu naught here. This integral of line integral of h bar dot dl bar is equal to I, where I is the current. Now you see, a current carrying conductor produces a magnetic field. Similarly, electromotive force, we studied this one as EMF in electrostatics. So EMF produces electric current and electric current produces magnetizing field. So as we call this EMF as electromotive force in electrostatics, this h bar dot dl bar is also called a magnetomotive force. To send some current through a circuit, we need EMF. Similarly, to produce magnetic field, we need current. That's why current is also called a magnetomotive force. So in simple, we denote this as MMF. Just like EMF, electromotive force in electrostatics, MMF, magnetic motive force, is equal to current, which is equal to the line integral of h bar dot dl bar. What are the applications of Ampere Circuital Law? Here, first let me use this Ampere Circuital Law in case of a solid wire carrying some current through it. So first case 1, solid cylindrical wire carrying some current. Let us say some current is flowing through this one, the current flowing through this one is I. If I want to find out magnetic field at different places here, so this is the center and we call this as the axis of this wire. And now if I want to find out magnetic field here, magnetic field on the surface and magnetic field here. So let me take 3 different points here. So I am going to draw the cross section of this one here. Here I am going to draw. So this is the wire cross section. This is the center through which the axis is passing. Now this is point 1, this is point 2 and this is point 3. So I want to find out magnetic field at point 1, point 2, point 3. Now as the current through this one is constant, that is the current density, we call it as J, is constant here. Current density is the current per unit area. Now, what is the total current that is passing through this one? So let me take the total current through this one is I. Through this small cylindrical portion, the total current passing through this one is I. Now, if you consider this one, so first I am going to take point 1. At point 1, so I am going to redraw this diagram here. This is the diagram. Circumference or the side view of this wire, and this is the point center. So this is point 1. The total radius of this wire, let us say this is capital R and this one is a small r. So in this case, what is the current density? This is the total current passing through this one by total cross sectional area. So this is I by pi r square. But what is the current that is passing through this one? This current passing through this one, let us say, let me take a small I. So current passing to the small circular portion is a small I, and what is the area of this one? Pi into r square. Here, as the radius is more, this current is more. As the radius is less, this current is less. Why? Because J is constant. That is given in the problem itself. So we can cancel this pi and pi. You can write the small I as capital I into small r square by capital R square. So this is equation 1. So I found the current that is passing through this circular portion only. Why? Because I want to find out magnetic field here due to this current only, and this current will not produce any magnetic field here. That's why I am not concerned this one. I am concerning current through this circular portion only. So now let me use this formula. Line of integral of b bar dot dl bar is equal to mu naught times the current enclosed by this small portion. So now you can write b is constant here because at same distance b will be constant to this current. So b line integral of dl bar is equal mu naught times the current enclosed here. So the current enclosed by the surface is I. So b into what is the circumference of the circular path? dl is equal 2 pi r. Why? Because if you see this one, this is a small portion. dl, if you add all these small quantities, then you will get total circumference as 2 pi r is equal mu naught times the, what is the current enclosed by this small portion? So this is given by the main current or total current passing to that wire into square of the radius of this small area by the capital 1. Now B is given by mu naught into I capital R square by, here you can cancel this R and R, you can write a small r only, 2 pi capital R square. So you can see in this expression, mu naught is constant, the total current is constant, 2 is constant, pi is constant, R is the radius of this wire which is constant. So B directly proportional to R. So if you increase the distance from this center to here, as R increases, the magnetic field due to this one also increases. Now second point is on the surface of this one, on the surface, that is case 2 at point 2, that is on the surface of cylindrical wire. So here what we can write, the line integral of b bar dot dl bar is equal to mu naught times the current enclosed with the Ampere'S loop. Now this will be the Ampere'S loop. The Ampere'S loop is the surface of the wire only. So what is the total current enclosed by this one is nothing but the I only. Now I am going to write b into the line integral of dl is 2 pi r, total circumference of this Ampere loop is 2 pi r, which is equal to mu naught times the total current enclosed, which is equal to the total current passing through this wire. So B is given by mu naught times of current by 2 pi r. So this is the magnetic field on the surface of a cylindrical portion. Now if you want to find out magnetic field at point 3, so once again we need to construct a Ampere'S loop such that the Ampere loop is passing to this point 3. So in case 3, that is outside the wire, cylindrical wire, now this can be written as b bar dot dl bar is equal mu naught times the current enclosed here. But here let me take this as x, distance from here to here is x. So this will become b into integral of dl will become 2 pi x into this is equal to mu naught times the, what is the current enclosed with a closed Ampere surface? Nothing but the total current passing through the wire only. So I can write I. So B is equal mu naught times I by 2 pi x. In some problems, especially in competitive exams, they may give this is also R, but R greater than capital R. Here this one R less than capital R. For this one, this R, here it is R less than capital R. B directly proportional to R. If R greater than capital R, that means instead of X I can take R only, but here R is greater than capital R. So this is R. Here if R distance greater than capital R, B inversely proportional to R. Here B directly proportional to R if the point is within the wire, and B inversely proportional to R if point is outside the wire, and B is equal to, if R is equal to capital R on the surface, and this is B inversely to R only. Now if you want to find the variation of field with distance, here what we can write, the variation of magnetic field with distance for a uniform cylindrical wire. So I am going to take this B along y-axis and R along x-axis. When R is equal to 0, that means at this point center, current will become 0. Why? Because see this one, if R is equal to 0 and B will become 0. So at R is equal to 0, B is 0. Now if you move away from this one, from the center, if you move away up by reaching this point or beyond this one in this direction, let us say this is a small r is equal capital R. So this is the variation of magnetic field. Why? Because B directly proportional to R. As R increases, B also increases. So this is a straight line passing through origin. In this region, B directly proportional to R. So after reaching the radius and beyond this one, outside the cylindrical wire, B inversely proportional to R. So the relation is a rectangular hyperbola. So you will get a rectangular hyperbola like this. So here B inversely proportional to R. Even this diagram was given so many times in the competitive exams. The relation between the magnetic field due to a cylindrical, solid cylindrical wire from center, and if you move away will be like this. And the other options will be given like this, and it may be given like this, it may be given like this, it may be given like this only. But the correct option is this. The next application, case 2, is magnetic field due to hollow thick cylinder. So this is a hollow thick cylinder with internal radius R. The external radius is capital R. So this is the cross section of this one, the top view of this cylindrical wire. So this is a hollow cylinder. Now if I wish to find out the magnetic field at different points, let me take this point as center of this one is 1, this point is 2, this point is 3, this point is 4, this point is 5. So if you wish to find out magnetic field at 5 different points, first point 1. So point 1 is not containing any material. This is hollow region and no current is passing through this point. Current is passing only through this material. So as there is no current, if you draw a small Ampere loop here, it will not enclose any current. So at point 1 the magnetic field will be 0. Now point 2, that is on the surface of the at a point in the inner surface of this hollow cylindrical portion. Here also magnetic field due to this current will become 0. Why? Because if you draw an Amperian loop through this point, even this loop will not enclose any current, because current is passing only through this material, only through the material between the second and fourth points only. So this is where the current is passing, current is passing only through this surface. So now if you draw any number of Amperean loops within the solid, this hollow cylinder, within this one, first loop, second loop, third loop, fourth loop, these loops will not enclose any currents. That's why current through first point, the magnetic field at first point or magnetic field at the second point, even if you take 7th point, 8th point, 9th point, somewhere here, this region will not contribute any magnetic field. Now third point is here, so point 3, so I am going to write this as a point 3, at point 3. So at point 3, what is the distance of this point 3? This distance is, let me take it as x. So x is greater than small r but less than capital R. Here x is less than capital R but greater than small r. This is the point. What is the total current that is passing through this one? The total current passing through this one is, let us say, I. This total current passing through this one is I. So as it is having uniform current density, when it is not mentioned, so J is constant. So total current passing through this hollow cylinder by total area, that is outer area pi r square, and subtract the inner area pi small r square, which is equal to, what is the current through this Gaussian surface? If you consider a Gaussian surface, Amperean surface through this point 3, so this is the Amperean surface here. So what is the current enclosed by this Amperean surface here? The current enclosed Amperean surface is given by I, which is equal to pi into, this radius is x, so area of this one pi x square minus r square. Now you can cancel pi and pi. Small I is equal capital I into x square minus r square by capital R square minus x square. So this is the current that is enclosed by this one. Now to find out the magnetic field due to this enclosed current, I am going to use Ampere's Circuital Law. Line of integral of b bar dot dl bar is equal to mu naught times the current enclosed by it. So this will be b integral of dl bar is equal to mu naught times the, what is the current enclosed here? This is the current enclosed by this Amperean loop, which is going to be total current into x square minus r square by capital R square minus x square. So this is this. So b is given by, what is the integral of dl bar? So this is the small portion. If you integrate this one, you will get 2 pi x. This is 2 pi x, which is going to be mu naught times of I by x square minus r square by capital R square plus small r square. So you can bring this one that side. So the magnetic field at point 3, because I am finding magnetic field at point 3, is given by mu naught times of current by 2 pi into x. This is x square minus r square by capital R minus small r square. So this is the magnetic field at point 3. Now if we wish to find out the magnetic field at point 4, then construct a Amperean loop through that point. So at point 4, now directly I am going to write this one. Line of integral of b bar dot dl bar is equal to mu naught times the current enclosed. What is the total current enclosed by this Amperean loop, which is equal to the total current which is passing through this one I. So this is b into 2 pi r is equal to mu naught times of I. So b is equal to mu naught I by 2 pi r. So this is the magnetic field at point 4. Then what is the magnetic field at point 5? So point 5, through this one construct an Amperean loop. So this will be the distance of this one from here to here. Let us say this is a y here. So b into at point 5, b into integral dl bar is equal to mu naught times the, this Ampere loop is enclosing the total current I. So this can be written as B into, what is the circumference of this Amperean loop? This is also 2 pi y, which is equal to mu naught I. So B can be written as mu naught times I by 2 pi y. So this is the magnetic field at point 5. Here also mu naught current 2 pi constant inversely proportional to y. So B, here B inversely proportional to R, here B inversely proportional to y. Here you can see these points. If you draw the graph between magnetic field and distance for a hollow cylindrical portion. So I am going to draw like this. This is the distance R and this is magnetic field B. Now up to this point, it means if you are moving from O to this point, magnetic field is 0. Then magnetic field will be constant and then magnetic field will decrease. So in this case also, as this is a given value, B inversely proportional to R only from that point 3. So you can write when R is equal to 0, magnetic field is 0 at first point. At the internal point also magnetic field is 0. And here when R is equal to capital R, that is at this point also magnetic field was 0. So up to here magnetic field is not present. It is 0 only. Suddenly from the third point what happens? Magnetic field rises to a value. So this is the maximum magnetic field. So after that magnetic field inversely proportional to distance. So this is a rectangular hyperbola. Here away from that coil it gradually decreases and here it will be 0. So after that it gradually decreases. So this is the variation of magnetic field with the distance. I am going to find out magnetic field due to a solenoid. First I am not going to use this Ampere's Circuital Law. I am going to use the magnetic field due to a circular current carrying coil. By using that concept I am going to find out magnetic field due to a solenoid. In the second method I am going to use the Circuital Law. So you can see that using Ampere's Circuital Law is easier than using this other concept. So here what I am going to do, I am going to take one solenoid here. This is a solenoid, long helical coil carrying some current, here I. Now in this case what I am going to take, I am going to take a point somewhere here. Let us say this is y axis and this is x axis. So this is point O. So here I am going to take a small strip of this one in the form of a circle. So this is the distance x and this is the radius of this solenoid R. So here the total number of turns we will check it. So what is the magnetic field at this point due to the circular current carrying coil here? The magnetic field at point O due to the circular current carrying coil is given by using that circular loop formula. This will be mu naught times the number of turns into I into R square by 2 into R square plus x square whole power 3 by 2. But what are the number of turns here? Let us say the total length of this solenoid is L. Total number of turns are N. The number of turns per unit length, we call it as a number of turns per unit length. This is total turns by total length. Here, if you know the number of turns per unit length, so for this 1 meter length, if it is n, what is the number of turns in this length? So total number of turns per unit length into that length dx. So here if it is x, this thickness is, let me take it as dx. So how many turns are present in this small portion? So this is n into dx. So I am going to write n into dx. Now here if you join these two ends, this will be root over r square plus x square. This angle is theta. Now what is the magnetic field due to the small strip? dB due to small circular strip is given by, here I got this value, mu naught into n dx, current passing through this one is I, into square of the radius by 2 of r square plus x square whole power 3 by 2. This is equation 1. If I want to find out the total magnetic field due to this solenoid at point O, due to the entire length of this solenoid, I have found only the magnetic field due to this width only. Total length I want to find out. So now we can write the total magnetic field due to the entire solenoid is given by integral dB, integral of mu naught into n dx I into r square by 2 of r square plus x square whole power 3 by 2. What are the constant terms here? You can bring them outside. So now mu naught is a constant. Number of turns per unit length of the solenoid is also constant. Current flowing through this is constant. Square of the radius constant. 2 into r square plus x square whole power 3 by 2 integral dx. But dx is the variable, so here x is also a variable. That's why I can write this as 2 outside. The remaining terms are r square plus x square whole power 3 by 2. The angle made by this edge with this point is O here. Now in this right angle triangle I am going to write tan theta is equal opposite side, that is x, by adjacent side, that is r. So we can write x is equal to r tan theta. This is one of the expression. If we differentiate this one, we can write. So let me take this as equation 2. By differentiation, dx is equal r of tan theta is secant square theta into d theta, equation 3. I got x value and dx value. I can substitute x value, dx value in this expression. Now the net magnetic field here is given by mu naught into ni r square by 2. This will be, what is dx there, which you can write it as r secant square theta d theta by, this will be r square plus x is equal to r tan theta, x square is equal to r square tan square theta whole power 3 by 2. So you can write this, you can simplify this one as mu naught ni r square by 2 integral r secant square theta d theta by r square common. You can take r square common, 1 plus tan square theta, directly I am writing it as secant square theta whole power 3 by 2. So this is mu naught ni r square by 2 integral of, this numerator is r secant square theta d theta by, in the denominator this is r square whole power 3 by 2 will become r cube, secant square theta whole power 3 by 2 secant cube theta. So this r and r get cancelled, secant square and secant square 1 will be cancelled there. So we have r square here, this r square also get cancels. That net magnetic field is given by mu naught ni by 2 integral of, you can see this one, this r square, r cube get cancelled, secant square, secant cube, we have only 1 by secant cube, which is can be written as cos theta d theta. That means I need to write the limits in terms of the angles here. Now if you join the first end of this point, first end of the solenoid with this point, let us say this angle is alpha, and if you join this point with the other end of this one, this angle will be minus beta. Why? Because here I measured this theta in this direction, so I am measuring this one in the same direction, this will be positive, and this is the angle measured in the opposite direction, this will be negative. So what are the limits here? The upper limit is alpha, the lower limit is minus beta. So now this can be written as mu naught ni by 2 integral of cos theta is sin theta. So sin theta with the limits alpha and minus beta. So you can write mu naught ni by 2 sin alpha minus of sin minus beta, minus of minus beta will become sin beta. So this is the magnetic field due to a solenoid at its center or at a point on the axis of this one. If the solenoid is infinitely long, for infinitely long solenoid, that means length is too high with the diameter. When compared to diameter, length of this one is too high. If it is infinitely long, then alpha will become 90 and beta also becomes 90, and if you substitute these values, magnetic field due to infinitely long solenoid, infinite solenoid is given by mu naught times of Ni by 2 sin 90 plus sin 90 here, sin 90 plus sin 90. So this is 1 plus 1. So this will become mu naught Ni by 2 into 2. So magnetic field due to infinite solenoid is given by mu naught times of Ni. So this is the magnetic field at the center of a infinitely long solenoid. Infinitely long solenoid can also be known as, this is also called ideal solenoid. In case, suppose if you take this point at one end of a solenoid, at one end of a solenoid of infinite length, that is ideal solenoid, then this alpha will become 90 but beta will become 0. So what is the magnetic field at one end of a solenoid? For one end of a solenoid, this will become mu naught Ni by 2 into alpha is 90, beta is 0. So we will get only one value here, sin 91, and sin 0 we know that it is 0. So magnetic field at one end of a infinite solenoid is given by mu naught Ni by 2. So based on this one, for an ideal or infinite solenoid, if you want to draw the variation of the magnetic field with length, at center magnetic field is maximum, which is given by mu naught Ni. So this is B, and its value is mu naught Ni at the center. And this almost maintains constant throughout its length, but at one end this value will become half of it. So at one end of this solenoid, value will be mu naught Ni by 2. This is the end of this one. Similarly at the other end also, this is mu naught Ni by 2. So after that the magnetic field gradually decreases and it almost becomes 0 due to this solenoid. So this is the variation of B with length. So here this is the middle of the solenoid. This is at the end. It is mu naught Ni by 2, and at the other end also, second end also, this is mu naught Ni by 2. And if you move away from the solenoid, the magnetic field gradually decreases and it almost becomes 0 at a large distance from the solenoid. We will derive the magnetic field due to a solenoid by using Ampere's Circuital Law. So in this case, what I am going to do, I am going to take the turns here in which current is flowing like this and it is entering here and it is coming out. So at these points, current is entering into the board. At these points, current is leaving the board. So I am going to take only those points here. This point, current is entering. So this is the first point, second point, third point, fourth point, fifth point, or fifth turn, sixth turn, seventh turn, like this. And at the bottom, these are the points where the current is leaving the board. Now in this case, the current is entering here into the board, into the board, into the board, into the board, and here current is leaving the board, actually leaving the turn in this case. So same diagram, I am just showing only these points, this point, this point, this point. So here current is entering into this one. Why? Because see, here current is going like this, it is entering here and it is coming out. So these are the points where the current is coming out. If you consider only that small elemental portion here, which is the elemental portion of this wire, so which is shown like this, here current is entering into this one. When the current is entering into this one, the magnetic field around this one will be produced like this. So for a current entering into the board, field should be clockwise direction. So this is the direction of the magnetic field. 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 Similarly here, as the current is leaving this one, field is in the opposite direction. Here field is opposite. Field is opposite. Here field is clockwise. Here field is anti-clockwise. The field produced will be anti-clockwise. So here this will be like this in the anti-clockwise direction. Now these are the first steps. Now if you want to find out magnetic field due to this current element at this point, so this will be in this direction. So here these fields will be combined together, and this field will be like this. So here field is in this direction. Here also, if you want to represent a magnetic field, here field is in this direction and field is in this direction at this point. Now you can see the next line will be like this. These are the lines. So this line will be like this. This line will be like this. This line will be like this. And this line will be like this. You can see these lines are acting in this direction as indicated previously. So the magnetic field strength is too large within the coil, that is within the solenoid, between these two. Here the field lines are acting in this direction, and here they are acting in the opposite direction. And one more thing is they are moving away from each other. That means a lot of space is there. So within this space the magnetic field strength is more. So we can write magnetic field strength inside the solenoid much greater than the magnetic field outside the solenoid. Now here what I am going to take, I am going to consider a Amperean loop here for this coil. So here I am going to consider one Amperean loop here, that is enclosing this current carrying elements. So here in the diagram, this Amperean loop is enclosing 3. So this I will take this side as first side of this Amperean loop, second side of Amperean loop, third side of Amperean loop, fourth side of Amperean loop. So what is this Ampere'S Circuital Law? Line of integral of b bar dot dl bar is given by line of integral of b bar dot dl bar for the first loop. So I am taking this as a first loop, plus line of integral of b bar dot dl bar for the second loop, line integral of b bar dot dl bar for the third loop, line integral of b bar dot dl bar for the fourth loop. Now you can see here the magnetic field is acting in this direction, and here outside the magnetic field is not there. Here even though it is acting in this direction, but the lines are far away from each other, and outside the solenoid magnetic field strength is too less. So here magnetic field in the first loop or first side of this Amperean loop, this value is almost 0, but not 0, almost 0. But when compared to these lines are spread away. So this strength of the magnetic field when compared to this one is very less. This I wrote here. Inside this one magnetic field is too strong, outside this one magnetic field is too weak. That's why we can consider this nearly equal to 0. So this value will become 0 here. The magnetic field outside this one is 0 plus. Second one, you see here the length of this coil is this one. The side of this one Amperean loop is this, but what is the direction of the magnetic field here? this I can take this as length, I can take this already, the length of the solenoid is taken as L. So I will take this length as along x-axis x, along y-axis let me take it as y. Now you can write this as B integral y, integral dl is y. But as it is a dot product, this is B dl cos theta. So cos theta for the second one, plus the third one B into this length is x, x into cos theta, and fourth one B into y into cos theta. Now you can write here the angle between B and y, how much? At this point field is acting in this direction. You can see this diagram, field is acting like this, but length is like this. Angle between these two is 90. So this will become 0. Similarly, in this case also length is this much, but field is acting at this point, field is acting like this. So the angle between B and y will be 0. So what is the net magnetic field now? Integral of B bar dot dl bar is given by, that means the second side, the fourth side will not contribute any magnetic field. The first one, this is first one, is also not contributing any magnetic field. Only the third side of the Ampere loop is contributing magnetic flux. So I will get only this one. So this will become B into, what is this x? So now the total length of this one is L. Let us say the length of this one is x. So what is x here? So I am taking this as x only, and here x is from here to here. Field is also acting in the same direction. Angle between B, so this is B, you can see this is direction of B, this is x, and both are acting in the same direction, cos 0. So this cos 0 will become 1. So this is Bx. This must be equal to, according to Ampere's circuital law, mu naught times the current enclosed by that closed Amperean loop. The total current that is entering into this one is I. What is the current that is passing through these strands only? Here, the total current is given as I. I current is passing through, total number of turns are N. Now, what are the number of turns per unit length? That already we wrote here. Number of turns per unit length is denoted with a small n. If you know the number of turns per unit length, number of turns per x length will be, this current I dash will be number of turns per unit length into the number of turns per unit length into width here x. So I can write this is I dash, current enclosed by only that loop. So B into x is equal mu naught into I dash will be n into x into the total current. So this is a total current here I, this is the current through this loop, which is equal to n into x, where n is number of turns per unit length and x is the total number of the total length here. So this will be nx into I. You can cancel this x and x here. Magnetic field will be given by mu naught times the total current. Magnetic field due to a toroid. So this is a toroid. Toroid is nothing but a closed solenoid here. So in this, let us say some current is passing to this one. So current is passing I. So this is the outer circumference, this is the inner circumference. Let us say this average radius is r. Now if you want to find out the magnetic field due to this one, now we can write line integral of B bar dot dl bar is equal mu naught times the current enclosed by the Amperean loop. I am going to take one closed Amperean loop like this. So within this loop, this will become B bar dot dl bar or integral dl bar is equal to mu naught times the current enclosed with the Amperean loop. So this is B into, this is R, the average radius. In some problems they may give this as A, outer is B. So R can be taken as A plus B by 2, average radius. Now this will be, directly they have given is R. So the circumference of the Ampere loop is 2 pi R, which is equal to mu naught times the current enclosed. Current passing through each turn is I. As it has a number of turns n, so current is entering n times in this closed Amperean loop. So I should write n into I. So what is the magnetic field here? Mu naught times of Ni by 2 pi R. Here you can see this n by 2 pi R is the total number of turns in this circumference. That is nothing but number of turns per unit length only.